Hi, I'm Robert Bevan. I work as a data scientist at the Medicines Discovery Catapult in the UK, and I'm here to present our submission to the NLM-Chem Track Challenge. In our entry, we focused on the PubMedBERT transformer model, which is a BERT model trained from scratch using PubMed abstracts and PubMed central articles. First, we fine-tuned a single PubMedBERT model using the NLM-Chem dataset. We then wanted to see if we could improve its performance using additional training data, namely the CDR and CHEMDNER datasets. Each dataset has its own set of annotation guidelines, so it's impractical to combine them into a single dataset. We decided to try training separate models using each dataset, and then train a stacking model to combine their outputs. We wanted to see if the model could learn to map the different label types to the new dataset, and leverage the additional training data to improve performance. The stacking model didn't do any better than the single PubMedBERT model fine-tuned using the NLM-Chem dataset, so we used a single model in the final evaluation. The NLM-Chem evaluation set contains many long passages. PubMedBERT can handle sequences of up to 512 tokens or word pieces, so in order to process long examples, we applied the model in a strided fashion and averaged the outputs. The table shows our model outperformed the baseline by a fair margin. We applied a sieve-based normalization approach in a similar manner to the baseline. First, we normalized each of the terms contained in the mesh database by lowercasing, removing white space, and replacing Greek characters with their English spellings. We then defined a set of string manipulation and substitution methods to be used in the normalization sieve. The string manipulation methods included stemming and non-alphanumeric character removal, and the string substitution methods included abbreviation expansion using AB3P and similar entity substitution using BioWordVec embeddings. The similar entity substitution approach works as follows. Given an entity, the 10 most similar BioWordVec strings according to cosine similarity are retrieved. Strings with a similarity score below some threshold are discarded. The remaining strings are then resolved to mesh codes where possible, and the final mesh code is determined by majority vote. We also made use of several synonym data sources, namely KEBI, UMLS, NCI Thesaurus, UNII, and PubChem. Our approach performs slightly better than the baseline in the strict evaluation, but we think this is probably due to the significantly improved entity recognition performance rather than an improved normalization procedure. We can see from the ablation study that the additional data sources were the most important component, and that the abbreviation expansion and similar entity matching components had little, if any, impact. For the indexing task, we trained a logistic regression model to predict whether or not each identified mesh code belongs in the index. We used the following features: mention count, normalized mention count, the number of passages the code appeared in, the number of passages broken down by passage type, for example, the number of times it appeared in the abstract, and the mesh code. Our system was more precise than the baseline system, but with much lower recall and a lower F1 score.